Any questions from last time? We talked about continuous random variables, calculated entropy, and said a little bit about how it behaves and KL divergence and so on. Okay. Also, I'm a little behind on notes, but I should be able to post a couple more lectures tonight, and also the second homework will go up either tonight or tomorrow. So you should be able to see it on campus. You should see an announcement soon. All right. So we talked about continuous random variables, and we computed entropy, in particular differential entropy for Gaussians, and so on. We kind of didn't quite get to do the calculation for KL divergence. So I wanted to just show it once before we start a new topic, which and then we'll kind of get to talking about applications to statistics. But just to say that the KL divergence for Gaussians, let's say if we have two one-dimensional Gaussian distributions with different means and different variances, then you can pretty much calculate the KL divergence from the definition, which is let's use the density functions instead of integrate over density functions instead of a summation. And yeah, I mean, if you kind of write log base e instead of log base 2, you get this kind of an expression, which if you think of it as an expectation of some quadratic functions, it's pretty much direct, which is we know that expectation according to the distribution P of x minus mu1 square is sigma 1 square anyway. That's just the definition of sigma 1. So that term is pretty easy to calculate, and this you can split, and this you can calculate by splitting into x minus mu1 and mu1 minus mu2 whole square, and then just plugging it into, just calculating the expectation of the two terms that come out of the summation should give a bound. This, as I said, is a relatively simple calculation, but I wanted to do it, one, because it's actually the most convenient way I know of understanding the statistical distance or the total variation distance between two Gaussians. So we said that because KL divergence is sort of a supremum over KL divergence is coming from finite setups, all the inequalities continue to hold, in particular Pinsker's inequality, which tells us the relationship between KL divergence and statistical distance or total variation distance. And so this is a fairly good way of estimating, let's say, so as an exercise, check if you have P, which is maybe mu1 and sigma square, and Q, which is, let's say, a slight shift of mu1. And for convenience, let's say the same. Okay, so the first exercise is, of course, finishing this calculation. And then if you have P and Q, which are just kind of slightly shifted Gaussians, then what can you say about the total variation distance or the L1 distance in terms of KL divergence using Pinsker's inequality, etc. Okay. And I mean, maybe even think about how tight is this. It might depend on epsilon. So okay. So Gaussian KL divergence is, because it's a much more analytic expression or kind of an easier to handle expression than the L1 distance. It's usually a common way of actually understanding if you were doing something with Gaussians. So again, the total variation distance is an upper bound on how much any 0-1 function differs on the two distributions. So if you had an algorithm which thought it was running on one Gaussian, but it actually ran on the other Gaussian, how much the behavior of that algorithm changes can be estimated from the KL divergence. And if you want, you can also calculate pretty much the same calculation.
Madhur?
Yeah.
You just said the KL divergence is a much more analytic expression. When you say that, do you mean like just more amenable to calculus?
Yeah. That's what I meant. Yeah. I mean, I guess both of them are analytic, but it's easier to kind of integrate or estimate small changes in or perturbations to the KL divergence.
Yeah, to just like stay put and compute things.
Yep.
Okay. Thanks.
Yeah, so I don't know if anyone was at the reading group talk yesterday, but there was a talk about clustering mixtures of Gaussians. And again, they kind of said if the total variation distance in Gaussians is large, then there are three kind of parameter distances, one of which must be large. And again, it's at least qualitatively, it's easy to see that using then sort of expression for KL divergence for Gaussians in n dimensions. So yeah, in case you're interested in that kind of stuff, to try to compute the KL divergence for n-dimensional Gaussians. It's a simple computation, but the expression is instructive. Okay, now let's move on to the applications to statistics, and we'll be back to discrete distributions or finite size universes for the rest of this lecture. And in particular, what I want to talk about today is something called method of types, which is just counting. It's just a fancier sounding name for it's a nice way to count things, and and in particular, it's a convenient way to prove various kinds of large deviation bounds or concentration bounds, sort of like Chernoff, and then we'll see that. But it also proves a nice result which kind of illustrates why KL divergence is the right quantity to use in various kind of concentration inequalities, etc. So this will become clear as we proceed through the lecture. But just to set up, we will deal with a finite universe, so the script X as usual. We will think of the size of it to be R. So throughout the lecture, R will denote the size of this universe. And the problems I'm talking about are even interesting for R equals 2. So you can think of R as fairly small and the number of samples n as going to infinity. Okay. So we'll draw a lot of samples from some distribution on this sort of small finite universe of size 2, 3, or small r. And we will think of the elements of X as just A1 to AR throughout the lecture. And we will get n samples, x1 to xn. Each sample will be equal to one of the AIs and will be drawn according to certain distribution, whichever we have in mind for the calculation. And just as a notational shorthand throughout the lecture, because I'll often need to write about n tuples or of samples, I'll just use this notation x bar, which will denote an n tuple. Okay. So I will not write x1 to xn every time I want to talk about n samples. And the type of a sequence of samples or a type of x bar is just the histogram. So if you drew n samples, how many times did A1 occur, how many times did A2 occur, and so on. So there are possible outcomes, how many times did each of them come up. And we will actually think of it as a distribution rather than kind of a collection of numbers, rather than saying how many times did A1 occur. You can ask what is the percentage or what is the fraction of times that A1 occurred. So we will think of a distribution piece of x bar, which is also called the empirical distribution. So it's just the number of times that this particular output A occurred divided by n. And we will think of, or I'll refer to this distribution as the type of X bar. Okay. So from now on, a type is a distribution. It's the empirical distribution. I'll also use the notation, the script Tn, to be the set of all types that can happen when I have length n sequences or n samples. Okay. No reference to any particular distribution, just any particular. So in particular, all the probabilities in such a distribution, which is present in these kind of types, should be a multiple, should be a multiple of 1 over n. So we can't, even if the size of the universe is 2, we can't quite have a type which is a distribution where 0 occurs with probability 1 over root 2 and 1 occurs with 1 minus root 2. Okay. And so you can check that, again, by just counting, this is just the number of times A1 can occur, number of times A2 can occur, and so on. So the collections of R natural numbers such that they add up to n total is just the size of this set T sub n. And you can check that it's upper bounded by n plus 1 to the R. And I also use C sub p to denote the type class, or rather the set of all sequences such that the type of these sequences is equal to p. Okay. And again, X bar will always be next to the n. All right. Any questions? We'll use this notation frequently throughout the lecture, so just emphasizing it a little bit. Any questions about the setup, the values of parameters? R is small, n is large, and there are some bounds here. Okay. And as I said, we will be kind of interested in questions of the following type, or well, of the form, but maybe questions of the following type is a bad part. But okay, we're going to look at, let's say, a sequence X bar, and we're going to ask, what is the chance that the type of this sequence, type of X bar, is in some set of distributions pi. Pi can be, so the distributions are over the set of values script X, right? Because the type is also a distribution over such, over this set script X. And in general, this collection pi need not be limited to kind of only things where probabilities are multiples of 1 over n. This can be an arbitrary collection. And we will be interested in this sort of probabilities as n grows. So we will consider many different values of n. So far, the question is not completely well defined, because I have to say, how are we sampling this X bar? Where is this X bar coming from? And so in these applications, there will be some distribution Q, okay, where again, Q is a distribution on the same space, and we will use Q to the n to denote the product distribution. Okay, so we are drawing n samples independently. And let me just state an example. So let's think of script X as 0, 1. Let's think of Q as the distribution, which is 1 with probability half and 0 with probability half. Okay. And let's say pi is the set of distributions, again, now on only 2 values, such that the probability of 1 is more than half plus epsilon. Again, note that I'm not requiring that pi is a collection of types. It can be any kinds of distributions. Potentially, this set could be infinite. Here, in particular, it's an infinite set. And yeah, just because epsilon is a real number. And so, okay, or the probabilities are real numbers. All right. And another way of stating this is that if I'm looking at x1 to xn, which are sampled uniformly, then what is the chance that summation xi is greater than equal to right? This is the same as summation xi over n is greater than equal to half plus epsilon, which is nothing but, if I look at the type of the sequence x bar, then the probability of 1 is just summation xi over n, or the number of times that xi is equal to 1. So these are the kind of questions that we have seen previously as Chernoff bound or as concentration inequalities. And so the kind of question I wrote above is a generalization of these. And we will be able to sort of say something about both upper and lower bounds on these kind of probabilities. And in some sense, it'll show sort of that KL divergence is between some appropriate distributions is the right way of measuring these probabilities. Okay. Any questions about the example before we proceed? All right. Okay. So we will need to do some form of counting to prove these bounds. And one of the kind of basic estimates we will need is just the size of a type class. So how many sequences x bar are there such that their type is equal to some distribution p. P is again an empirical distribution. So and if you recall, we were looking at, or in, I think one of the first 2 lectures, we kind of estimated what is the number of sequences such that maybe the of n zeros or ones, such that the number of ones is exactly k or at most k, or we kind of computed estimates on binomial sums. And there we obtained a bound in terms of entropy. This is again a generalization of that, because instead of just saying what is the number of ones or zeros, you are saying there are r possibilities, how many times did each one of them occur. So it's not surprising that entropy is a bound, and we can prove the general bound just by some relatively short computations. So you can write this in terms of probabilities or counting. I prefer to write this in terms of just kind of counts. So let's just calculate n to the n in 2 different ways. And before that, actually, let's say P is a type, which means that the probabilities are multiples of 1 over n. So if, let's say the probability of A1 is some k1 over n and so on up to k sub r over n. And yeah, some of these can be 0, sort of, but they are but they're non-negative. And we can sort of just think of, because the probabilities add up to 1, we know that summation ki is equal to n. And so we can just expand the expression on the right, which is just summation ki to the n. You will get some multinomial expression here. And we'll use a simple bound, which is, okay, so first of all, I should say that I'm only going to prove one side of the inequality I claim, the slightly harder side. So I'll leave as an exercise. So I'm proving the lower bound for now. Here we'll just kind of estimate this term or by saying the right-hand side is upper bounded by the number of terms times the largest term. Okay, and The number of terms, okay, so we'll get to the number of terms in a minute, but I'll actually give the computation of the largest term as an exercise, but let me state what it looks like. So okay, so for each choice of J1 to JR, there is some term, and my claim is that the largest one actually occurs when each of the J's is equal to the K's. You can again think of it as a generalization of the fact that if you're computing a binomial expression, the highest weight is on the middle term where you have half zeros and half ones, or these are just, yeah, okay. I can state more intuitions for this later. But a simple way of checking this is just to say that if this is not the case, then there must be some J which is lower than the corresponding K, and because the sum is fixed, there must be some J which is higher than the corresponding K. And then try to see what happens if you kind of move up one of them by one and move down the other. And yeah, that's usually informative in terms of how to prove this. Okay, so I'm happy to discuss this more later, but or feel free to ask me if you have a question, but otherwise I'll kind of assume about the largest term. Okay, so now let's say we fix that the largest term is when all the J's are equal to the corresponding K's. So I've just written out that term. And now I need to know the number of terms. Any guesses about what the number of terms is? So I'm looking for the number of J1 to JR such that we've already seen, good, okay, n plus 1 choose R. Yeah, it's almost that, but it's whatever is the number of types, right? Because it's just how many ways can you add up integers so that the total is add up to n, so the number of histograms. And we already kind of claimed a bound a couple of slides earlier. It's n plus R minus 1, choose R minus 1. It doesn't matter. It's upper bounded by n plus 1 to the R, as we said, but this is a more precise bound in case you're interested. All right. Once you do this, it's a relatively simple kind of bound after that. So we got that n to the n is less than equal to, we proved a bound which is of the form n plus 1 to the R over this. N factorial over k1 factorial, rather this term, is actually the quantity we are interested in bounding, which is the size of the type class corresponding to the histogram with values k1 to kr. Right? So this is just a way of kind of distributing n integer sort of n boxes and or n bins and filling one, sort of one with k1 balls, k2 balls, and so on. So that's the quantity which we are interested in estimating. And for the rest, let me actually divide on both sides by n to the n. So okay, so all I did was I just sort of moved the n to the n from the left to the right and split it in among all the terms, just because summation of like k1 plus k2 all the way to kr is equal to n. And now this looks sort of like what we want, and let's just finish the calculation. this is nothing but the entropy of the distribution P, which corresponds to the type. Negative because we have the probabilities inside the log rather than 1 over the probabilities. And then, yeah, just rearranging the terms tells you that the size of the type class is greater than equal to 2 to the n times h of P. And I'll leave the upper bound as an exercise. You can do it using the same proof, or you can use some of the ideas from our earlier bounds or binomial sums, whichever you like. Okay. But okay. And once we have this, we kind of can pretty much do the computations needed to the binomial to the sort of probabilities we want. Just one sort of general comment before that, that the type is a good way of calculating the probability of a sequence for any product distribution. So if I have Q, which is any distribution, not necessarily a type, just any distribution whatsoever, and if I'm sampling n samples independently, and if I want to know for a sequence X bar, which is what is the probability of the sequence according to Q, all I need to know is the type of X bar. So if in particular, if the type of X bar and type of Y bar are the same, which means that they have the same histograms or same empirical distributions, then their probabilities will also be the same. And it's not too surprising. It's just the fact that if you look at the sequence X bar, it's nothing but independent probabilities of each of these terms. And each of the term only depends on whether it's A1 or A2 and so on. There only are possibilities. So it's just so it's just because each term of the product only depends on whether it's A1 or A2 and so on. So in particular, if all the terms are A1, then the probability will be Q of A1 to the N. I guess there's only one sequence of that type, but if you have two different sequences. So yeah, just like before, if you're tossing coins, then if you have a sequence with the same number of heads, then its probability will not depend on where those heads occurred. And we used this previously to say that if you have two distributions which kind of maybe differ in the probability of heads, and if you're trying to predict which distribution the sample is coming from, then the number of heads is a sufficient statistic. Or and this we saw as an exercise when we were talking about sufficient statistics. And here you can in general say, using the above, that the type of a sequence is a sufficient statistic. So if I had two distributions P0 and P1, and then we'll use this quite a bit when we talk about hypothesis testing, where we would want to figure out whether the true distribution is P0 or P1. And the fact that the type is a sufficient statistic means that we can just basically only design tests which look at the type of a sequence and not really many more details about it. And that will automatically tell us what our tests should look like. Any questions? All right. Okay, and now kind of almost ready to kind of estimate the probabilities we want. So we want to check if you are truly sampling from Q. Again, Q is arbitrary, it not necessarily a type or anything. What is the chance that your sample looks like P? So it truly came from Q, but it looks like P in the sense that the type is equal to P. Or if it's in the type class. And my claim is that this probability is basically 2 to the minus n times the KL divergence between the two distributions between P and Q. And maybe this is already starting to look a little bit like the kind of Chernoff bounds we talked about, but we'll say a little more about this in a bit. Here, Q is arbitrary, P is a type, and we are just trying to see what is the chance that the type of the sample is equal to P. I mean, the computation is relatively straightforward based on what we just said. So the probability that the type of the output sequence is equal to P means that we just kind of add up all the, write down all the output sequences and right. So, and we just add up all their probabilities. And based on what we just saw, the probabilities of all sequences of the same type are the same. So, so all these terms in the summation are all equal. So the number of terms is equal to the type class. That's sort of how we defined it. And we just want to compute the probability for any term. We just proved that the probabilities are equal for all terms. And we also already estimated the size of the type class. Now, we'll kind of compute it in two steps. So let me maybe write it out on the previous page first. It will be, just because the size of the type class is also related to the entropy, it will be convenient to do this computation by computing what is the probability according to P and what is the ratio of the probabilities according to Q and according to P. So of a fixed sequence X bar, which is of type P. And okay, let's do this computation. Okay. So the first claim is, according to P, the probability is just 2 to the minus entropy. And both of these are equalities. We don't even need to kind of estimate this. And this is again relatively direct computation. So so we know that this probability is equal to probability of AI times the number of times that AI occurs. And because P is a type, the number of times AI occurs is n times its frequency, or so of n. That's the number of times it occurs in the histogram, n times its probability. And yeah, I mean, it's sort of again the same thing as before. It's 2 to the summation over I. Oh, sorry. Yeah. It's exactly the same computation as before, which we did with the KIs. It's nothing very different. Pretty much the same argument also shows you the ratio of the two probabilities according to Q and according to P. So it's just a little more involved computation, but you can see that this is equal to the probability according to Q will be Q to the AI, of Q of AI to the number of times AI occurs, and according to P will be P of AI times the number of times this occurs. And again, as before, it's just kind of change the product to a summation in the exponent, and you get okay. Any questions so far? Okay, and let's just check that this proves the theorem we wanted. So maybe going back here. We proved bounds on both these quantities, so let's plug that in. And okay, it's and we proved upper and lower bounds on the size of the type class, which were either of the form 2 to the n times h of p and greater than equal to 2 to the n times h of p divided by n plus 1 to the r. So once you plug in the bounds on the size of the type class, you get the two bounds on the probability that if you sample something from Q, type looks like P. Okay. So as you said, it's basically counting, just sort of carefully counting in terms of just how many things are there of a given type. And if you break the counting in terms of that, the probabilities are relatively easy to compute. Okay. Now let's see a couple of applications, or maybe at least one application of this. Which is, again, let's just go back to Chernoff bound. Can you tell me the probability we have here in terms of what we have computed so far? Any suggestions? So the universe is of size 2, it's either 0 or 1. Q, let's say, is the uniform distribution as before, 0 or 1 with probability half. P is this sort of biased distribution. Let's say the probability of 1 is, yeah. Kevin, do you want to say something or no? Seemed like you were raising your hand while writing something. Okay.
I was moving my lamp.
Sorry. So, okay. So as I said, the question doesn't quite correspond to what I proved before, because we estimated the probability when P was a type. So from what I've said so far, it's not obvious that this is a type. So let's say is a multiple so then this distribution is a valid type, and we can ask these questions. Any suggestions now? And by the way, this assumption is also coming from here. Otherwise, the probability will be 0 because the number on the left is an integer. And so half plus epsilon better be a multiple of 1 over n. Otherwise, the right-hand side will not be an integer and the probability will be 0. So the sum of integers can only be equal to an integer. Okay. Anyone? Okay. Either this is obvious or maybe I lost you a long time ago, but in either case, let me remind you. It's this is a question which we already posed before, because this is just the probability of 1 being equal to half plus epsilon in the empirical distribution or the histogram of the output x. So all we are asking is that what is the chance that the probability of a uniformly chosen sample that p of x bar is equal to p, which is the distribution where we have half plus epsilon fraction of ones and half minus epsilon. And we already proved that this is actually upper bounded by the KL divergence of the two distributions. We computed the KL divergence of these two distributions when we were talking of distinguishing biased coins, and we got that this was some constant times epsilon square, or it was upper bounded by some constant times epsilon square. I guess lower bounded here. And we can also prove a lower bound on this quantity, which is in terms of. So you can observe a couple of things. One, there is a very good reason epsilon square. So first of all, this is sort of like the Chernoff bound, although it's not quite the Chernoff bound. Anyone wants to say why, or what's the problem? The probability I computed is sort of looks like the Chernoff bound, but not really. Or it's not quite a concentration bound yet. Okay, the issue is this equal to. In concentration inequalities or in Chernoff bounds, we'd like to say that what's the chance that it's greater than equal to this? So not just precisely equal to this number, right? And we want to just say that it just cannot be anywhere larger than this number. It has to be smaller. So that's one issue. And actually here, that's not so hard to resolve, at least if you are interested in the upper bound. So okay, so I claim that here I can actually get a Chernoff-like bound just using what I wrote on the previous line. So sure, the right-hand side has to be something which is maybe greater than equal to half plus epsilon times n, but there are only n choices. In fact, even n over 2 choices, right? So the right-hand side is a number between 1 and n, in fact, and sort of about n over 2 and n. So there are only n over 2 choices. For each of those choices, the above bound will tell us that the probability is at most 2 to the minus n times the KL divergence of p q, because for the other choices, the type will be something where the number of ones is even larger, so the KL divergence will be even more, and we'll make this precise in a bit. And there are only n choices, so we just get an exponent, we just get a factor of n in the front. Now it is a Chernoff bound, and a couple of good things specifically this quantity can tell us. One, in Chernoff bound, we have an epsilon square in the calculation, and here it sort of says that there is a very good reason that epsilon square appears in the exponent, because it precisely is the KL divergence of these two distributions which we are trying to distinguish. Okay. And second, although the previous bound only estimated the probability that the type is of a sample is equal to p, we can actually get a bound against a large collection of types, or sort of anything greater than half plus epsilon, not just equal to half plus epsilon times n, by just using a simple union bound. So we can recover a Chernoff-like bound, and then more generally, but it sort of also tells us how to generalize, or what was missing from the previous calculation, not just saying it's equal to one type, but it maybe belongs to some collection of types. Okay. And this is the content of what is called Sanov's theorem, and this is the finite case of Sanov's theorem, which is kind of an important theorem in large deviation theory or this kind of concentration bounds. And the proof is basically what we just said so far, but let's make it precise. So I'll state and prove the theorem in two parts, in the upper and just again observe on the previous example that this 2 to the minus n times epsilon square were not just an upper bound, but also a lower bound. So it also tells us that the Chernoff bound is tight, at least if you are only interested in the exponent. So the probability is also lower bounded by the same number, okay, or almost the same number. And all of these things kind of hold in more generality. So let's prove that in Sanov's theorem, and we'll use this theorem later in various applications to hypothesis testing, etc. Any questions before we proceed to this? Okay. So okay. So we want to prove now an upper bound. The upper bound proof is exactly the kind of union bound we just did, but let me first state the formal content of the theorem. So let's say now we are given a collection of distributions. Let's call this set pi. These are not necessarily types. In fact, n is not fixed. This is and the collection may be infinite. Again, as on the previous page. And we want to upper bound this probability, which is sort of a generalization of the statement to the Chernoff bound, that the type of a sequence sampled according to Q, and Q is again an arbitrary distribution. What is the probability that the type of the sequence belongs to this set pi? Okay. And I claim that the probability is essentially governed by, some sense, the closest distribution closest distribution P in pi, which is the closest to Q. And the notion of closeness is defined by this KL divergence. So and saying it's governed by P, which minimizes the KL divergence P to Q, P in pi. The reason I'm writing it in this way rather than in terms of this actual closed distribution is because the minimizer might not exist in the set pi. The set pi might be an open set or something where you can approach a bound as closely as you want, but not attain it inside the set. So let's say, formally speaking, let's say if delta is the minimum or the limit of the minimizing sequence for P, the KL divergence of P and Q, then the upper bound is in terms of 2 to the minus n times delta. This delta is also sometimes referred to as the KL divergence of the set pi with respect to Q. This is just a piece of notation. There is nothing, there's no new definition about the KL divergence of a set of distributions with respect to another distribution. It's just whatever is the minimum value. All right. Any questions about the statement? The proof is basically what we just said. So if you are sampling X, which is a sequence of length n or X bar, then the probability that the type is in pi is equal to the probability that the type is in pi intersection t sub n, because it has to be a valid type. So it can only be a distribution which arises from length n sequences. Okay. And then you can just kind of go over all the distributions which so pi itself might be an infinite set, but if we are saying something about the outcome of length n sequences, then the only elements of pi that matter, at least for the upper bound, are the ones that can be realized by the length n sequences. So it's just and we just sort of once we are summing over all of this, we can we know that this probability is upper bounded by 2 to the minus 2 to the minus the KL divergence of P and Q. N times the KL divergence of P and Q, and we know that the KL divergence is at least delta, because delta is the minimum or the infimum. And the number of terms is just less than the number of types, which is plus 1 to the r. So it's basically the same proof as before. Earlier we said that for every fixed outcome on the right hand side, the probability is at most 2 to the minus n times epsilon square, and there are only n possibilities. This is sort of the same proof, just carried out in a bit more generality. Okay. Any questions about this before we proceed to the other side of the theorem?
I feel like we've done nothing, but we have concentration. It's very nice.
Right? Yeah, so the method of types in that sense is kind of a very simple proof of a fairly general concentration theorem. So, I mean, all we did was just basically some very simple counting. I swept a little bit under the rug by giving some exercises, but those are not difficult exercises. And but once we do that, we get this kind of super strong and fairly general concentration, for even potentially infinite collections of distributions. And not just that, but the kind of, in some sense, the right exponent, because in a minute we'll also prove a lower bound. So it's sort of essentially tight in general concentration. The caveat, of course, is that it's very important that the samples x1 to xn are all independent. And there are many concentration phenomena which do not require independence. And the method of types, as we sort of said, says nothing about them. If there's some other dependence, we'll have to use other techniques to prove concentration. This is purely just a convenient way of counting, which works when you have independent sequences. But otherwise, yeah, it's a fairly, at least something which kind of explains the role of KL divergence in concentration fairly cleanly. Okay. Any other questions? Yeah, that's pretty much the feeling. We kind of didn't really do much, but it gives concentration. Okay. The other side of the theorem needs to be stated a bit more carefully. So, in general, we can't always expect a lower bound on this kind of probability that the type is in pi for arbitrary sets pi. Okay, so, as an example, if your pi only had this one distribution, which is, let's say, 1 over root 2 on the value 0 and 1 minus 1 over root 2, then no matter what n is, the probability of the type of a sequence being equal to this one distribution is 0. The probability of this particular distribution being as the type of anything or something landing inside this one element set pi is always 0. So there is no lower bound. So for a general pi, there cannot be a lower bound. And the way we kind of avoid this problem is by saying that, okay, maybe pi is not quite this, that you have just sort of one bad point and sort of no rational numbers close to it, so that you can actually have those distributions as valid outcomes. So the way you avoid this is by saying that pi is sort of basically an open set. So an open set is something where around any point you can find like a small ball. So in particular, you can find, and you can think of the natural topology on real numbers. It's just an r-dimensional vector. So you can just think of the kind of notion of open and closed sets there. But then just an open set is not enough, because we will, like, now we are trying to kind of somehow get to this infimum value or get as close as we want. So we will need sort of some form of closure, and then we'll see in a second. But so what we basically say is that it's the closure of an open set, or it's sort of it's a closed set which has an interior. So it's the closure of its interior. If you want an even nicer conclusion, that not only is it equal to this minimum KL divergence, or sort of say something depending on this minimum KL divergence, but in fact this value is attained and there is some sort of minimizer P star which minimizes this sort of KL divergence of P with respect to Q, and this P star exists in the set, then you need to add more conditions. Maybe if the sort of pi is compact or something, then you'll have this. I'm not stating that. But at least for the lower bound, we will need some additional guarantees. I just want to mention that because of this sort of weird counterexample with irrational probabilities, which just cannot happen. Okay, so let's say that it's basically an open set, if you want to think of it that way. And the way,
sorry, Madhur, can I ask a question?
Yeah.
Sorry, is this labeled part 2?
Yeah, part 2. I mean, it's just part 2 of Sanov's theorem. It's, I mean,
so this is this an wait? So is this an assumption? Wait.
Well,
no.
The first line is an assumption. The second line is a conclusion.
Yeah, and then you need this to show the lower bound. Like, why should I? I'm like not seeing why I should care about part 2.
Yeah, it's for the lower bound. Sorry. I mean, actually, you can just sort of look at the statement here and see that it actually implies the statement on the previous slide. So because the probability after this kind of 1 over n log, etc., it kind of tends to some quantity, just means that the probability is upper and lower bounded by 2 to the minus n times whatever was the quantity there on the right hand side. So it implies that, but I just want to emphasize that the upper bound always holds for all pi. Okay? There is no assumption on pi. When pi is basically an open set or the closure in open set, the upper bound is nearly tight, at least if you only care about the exponent. Okay? So that is why I'm kind of stating it in this two-part way, that the upper bound we could prove without any assumptions whatsoever. And if you make these relatively benign assumptions, then the upper bound is actually sharp. And I mean, the kind of examples are just these kind of pathological examples where the probabilities just cannot be realized or some weird things like that. But if you just allow me to move around a little bit from my probability distributions, which is available in this open set assumption, then I get a lower bound. Okay?
Thanks.
All right, so the way we will kind of prove it is just maybe now choose a sequence of distributions, which I'm sort of denoting by p superscript n. And I'm using the same parameter n as the number of samples because we will think of n as the number of samples we will draw from p superscript n. And let's say this is the probabilities are multiples of 1 over n. So this is in the type class t sub n, intersection pi. Okay, so and the KL divergence tends to whatever is this minimum value we were looking for, delta. Okay. And now we can sort of basically apply the bound for each of these distributions p superscript n, and then just take the limit. So let's do that. So we are interested in the probability that a sequence has the property that the type is in pi. We already proved an upper bound, which is of the form 2 to the minus, I guess, n plus 1 to the r times 2 to the minus n times delta. Okay, so I'm calling this quantity again as delta, sort of as on the previous. So the upper bound we already proved, so I'm just going to write it here. For the lower bound, now I will prove that this is lower bounded by the probability that the type is equal to this particular sequence p superscript n. Because we're trying to calculate the probability that it's any element of pi. So in particular, this one element of pi should give us a lower bound on the probability. And when we are looking at a specific element, then we can use the lower bound that we had before. Which was just in terms of just in terms of the KL divergence now of this element p superscript n with respect to q. Now, all that kind of remains to be done is just take logs and take limits. So let's do that. So let's write down the quantity we are interested in calculating. And what we just proved is that this is less than equal to delta minus, minus delta plus r times log n plus 1. And greater than equal to minus delta plus. Okay, not quite minus delta yet. Times minus. Okay, and now if we take limits on both sides, we get what we want. The log terms, because there is an n dividing them, they just kind of go to 0 as n tends to infinity. And so the limits on both sides, so if this goes to 0 and this goes to 0, this goes to delta, and this is already delta. So we get what we want just by taking limits on both the sides of the expression. Okay. All right, so that's Sanov's theorem, which in general lets us estimate the probability that if you sample according to Q, the outcome is in fixed or is in some set pi. Okay, any questions about this? Okay, so that's sort of all that I was planning to cover in terms of results. Let me make a couple of remarks since we have a little time right now. So Sanov's theorem also extends to infinite setups. To continuous random variables. And now, I mean, basically things carry over because, as we said last time, the KL divergence is a limit of, or is a supremum of KL divergence when computed for finite variables by just kind of partitioning your space into a finite number of pieces and just thinking of distributions over finite universes by just kind of adding up the probabilities over each piece. So the results are in terms of KL divergence. KL divergence is a supremum of finite quantities, so the same kind of bounds carry over. But it's a bit weird if you think about it, because we were talking about types or histograms and so on. And in particular, if you have infinitely many values, then the histogram will look pretty kind of useless. Almost everything will appear. If it appears, it will appear pretty much once. Otherwise, it just won't appear. So it's not clear what it means to think of histograms, or why should we talk of or types when we are talking of infinite universes. But the point is, a lot of the action is actually hidden inside the definition of pi. So maybe you are interested in some two distributions. So let's say you have some sort of two distributions P1 and let's say P2, or maybe a few. And you are interested in saying what is the chance that the type of sort of n samples from an infinite random variable or continuous random variable is equal to or is in some set. So it doesn't quite make sense to say it's in the set P1, P2, P3, because the type will not be equal. But you can sort of define pi to be some sort of ball around each of these sets in whatever is your favorite notion of distance. So it could be L1 distance, it could be some form of KL divergence, it could be some other distance on distributions, it could be saying that the moments are approximately close, whatever is your favorite notion for the application. And so it's kind of, instead of saying that the type is in a ball around some set, or sort of a union of balls around some set, you can also think of it as saying, if your distance is symmetric, you can also think of it as saying a ball around the type is in some set, or intersect some set. And even if the type doesn't quite make sense, if you have kind of infinitely many values, balls around a type sequence or just kind of, if you allowed me to perturb the distribution a little bit, then it makes a lot of sense. So like the statement generalizes to infinite universes, but then it's sort of the choice of pi is what really determines how you apply it, etc. Another is, what is the kind of, like, we sort of started with saying you're thinking of distributions on this finite set 0, 1 or something, but it's not just about Chernoff bounds or just about, so an example which, and we will talk about hypothesis testing in general, but an example which you can think of is, let's say you have some set of labeled examples, or let's say you have some sort of examples where you're trying to learn some kind of a classifier. So you have x1, y1, and let's say you have a classifier in mind, say f, and you learn some sort of loss function. So okay, so you have some, let's say, a half space which is classifying points sort of as plus or minus 1, or any sort of classifier where you are thinking of a loss function as maybe taking some finite number of values, or you can discretize if you like. Okay. And we can think of this as a distribution, which is just saying that, which would be the kind of true distribution if f was the classifier according to which the losses were coming from. So you could have had a classifier f0 or f1. You could have had a classifier f2. Or you could have had a classifier f sub t, let's say. And so you can think each of these rows as n samples from a distribution which is, let's say, P1 in this case, or P sub t in each of these cases. So for each classifier, you can think of a distribution which is giving you the losses if according to that classifier. Okay. And in some sense, if you're trying to kind of minimize or find the best classifier for something, you can think of them as samples from one distribution or another distribution, or sort of according to each one of these classifiers. And you can be interested in distinguishing what is the chance that the best classifier is f1, but my distribution looks like the best classifier is f2, or it sort of looks like it's coming from one of these other distributions. So just because you're not actually seeing the classifier, you're only seeing the losses. And maybe f1 was a really good classifier, which means in truth, the samples from f1 only look like mostly zeros. It's a really good classifier. It doesn't really make errors. But you're seeing a lot of ones, which would have happened if you picked the wrong classifier, f2, but not if you picked f1. But can it happen that the samples were actually classified according to f1, but they looked like they were coming from f2? And in these applications, it's not that someone will be giving the samples to you. They'll be, I mean, you'll be applying possibly these classifiers yourself and computing the losses, etc. But these will be used in what are called generalization bounds. It's also used in hypothesis testing, where, again, we want to distinguish what is the true distribution for data. You are given samples which comes from one of them. And again, you can think of the hypotheses as saying, this is the best way to learn my data, or this Gaussian has mean mu1, or has mean mu2, or has mean mu3, and you want to classify. And you can think of them again as samples from different distributions, and you want to understand what is the chance that the sample was actually from one distribution, but I kind of mistakenly thought it came from another. And that's what Sanov's theorem is roughly capturing, that KL divergence is the quantity which determines this kind of probability. So we'll see more applications. Maybe I'll stop here for today and take questions.